All right, we are looking at solving quadratic equations. So we just looked at linear equations, and we're going to look at quadratic equations. We're going to use the zero product property to help us solve quadratic equations. So first we're going to talk about some forms a quadratic equation can take. So this is called the standard form for a quadratic equation. It's in the form ax squared plus bx plus c equals 0. That is important that it equals 0, where a, b, and c are some real number. So a, b, c can be any real number. When we factor that, and we did this in chapter 1, we typically get, at least a trinomial like this, we typically get something that looks like this. We have something plus something and something minus something or something plus. We have two different factors that we can factor this into. And it tends to either be a plus or minus, and the n and the m are just placeholders. So don't concentrate so much on what the n and the m are. I just threw some random letters in. But we factored into two groups, into two factors, equals 0. It also tends to look like this, where we're able to factor one item out of a binomial, and we could get something like this. So this is if we're going to pick a form, these tend to be the way factored quadratics look. What we're going to do with that, because that's really chapter 1, is we're going to use that to help us solve for x. So here's the zero product property. Zero product property says if something times something else, if r times s equals 0, then either r equals 0 or s equals 0, which makes sense. If r times s equals 0, one of them should be 0. One of them needs to be 0, or both of them. But in that case, it wouldn't really matter. But at least one of them has to be 0 to make the product equal to 0. So if we look back at our factored form here, if n plus m times n minus m equals 0, then either n plus m must be 0, that'd be that r piece, or n minus m equals 0, that s piece. So one of those has to be 0. And we're going to use that to help us solve for x. So we're going to basically take this quadratic, we're going to factor it, and then we're going to take these two factors separately and say, well, if the product of those two factors equals 0, one of them must be 0. We're going to use that to help us solve it. Same idea with this other form of the factored quadratic here. Either g would be 0 or t minus r would be 0. Because again, we've got a product of two different factors and they equal 0. One of them has to be 0. At least one of them. Let's do an example to see how this plays out. So we've got x squared plus 6x minus 27 equals 0. We've got this quadratic equation. It's in standard form. It equals 0. You'll notice the leading coefficient here is 1. There's no number out in front of this x squared. So I can use a faster method of factoring this. I don't need to use the AC method. I can ask what are two numbers that multiply to negative 27 that also add to 6. So I know that positive 9 times negative 3 would be negative 27, and positive 9 plus negative 3 would be positive 6. So my two factors would be x plus 9 and x minus 3. Once I've factored it, because that's chapter 1, once I've factored it, I can use that, the zero product property, to say if x squared plus 6x minus 27 equals 0, if that's true and I want to solve for x, one of these two factors has to be 0 to make that product equal 0. So either x plus 9 equals 0 or x minus 3 equals 0. So essentially, I've taken this quadratic equation and I've factored it into two linear equations, x plus 9 equals 0 or x minus 3 equals 0. And the only way that works is if it equals 0. Well, x would have to be negative 9. Negative 9 plus 9 equals 0. Or x would have to be 3, because 3 minus 3 equals 0. So those would be my two solutions. And you are going to typically get two solutions. Not always, but typically you're going to get two solutions. And if you plug that in, 3 squared plus 6 times 3 minus 27 does equal 0. And negative 9 times negative 9 plus 6 times negative 9 minus 27 equals 0. So if you plug those back into the original equation, it does work. Take a minute, pause the video, and try to solve this quadratic equation on your own. I'm assuming you paused it. I'm assuming you tried it on your own. Again, watching me do it is not the same as doing it on your own first. Try it. Even if you're struggling with it, do something with it, see what you can make of it. And then if you get stuck, continue watching. So I'm gonna show what it factors to. I'm gonna show the process here. So factoring it, -2 times -7 is positive 14. -2 and -7 add to -9. One thing to be careful of, the factors are -2 and -7, but the solution is not -2 and -7. -2 times -7 does give us a positive 14. -7 plus -2 does give us -9, but something minus 7 equals 0, and something minus 2 equals 0. So the solution set is not the same as what we do when we're factoring it. We have to then ask, x minus 7 equals 0. Well, x would have to be a positive 7. X minus 2 equals 0. X would have to be a positive 2. So when you're factoring this, don't go so fast that you just write down the factors. Take a moment to write down those factors and ask something minus 7 equals 0, something minus 2 equals 0 to get those solutions. Factoring by grouping. So now we're looking at a bigger problem. This is actually not a quadratic. This is a cubic. We've got an x, p to the third power, p to the second, p, and p to the 0. So we've got a bigger problem. We are not going to spend a lot of time working with cubics. We will in, I think, chapter 6, spend some more time with cubic equations. We're going to concentrate more on quadratics. However, we can deal with a cubic in a certain way. And so if the problem works just right, we can deal with it using what we currently know. And so that's, if you see a cubic in the homework, if you see a cubic equation in the on a quiz or a test, it's going to be in this form. And so it's going to work using this method of factoring by grouping. And here's how factoring by grouping works. What we're going to do is we're going to ignore the second half of this quadratic or this cubic equation. We're going to ignore the 16, 32, and 0. We're just going to concentrate on the first two terms, 9p cubed plus 18p squared. And we're going to ask, what can I factor out of the first two terms? I can factor a 9 out of both of them. I can divide them both by 9. And it looks like I can factor p squared, 2 p's, out of both of these. So if I do that, if I factor out a p squared from both of those terms and factor out a 9 from both of those terms, I'm left with this. You can check that by distributing back through. 9p squared times p is 9p cubed. 9p squared times 2 is 18p squared. Okay, so I factored the first two. Now let's see what I can factor out of the second two terms. I can't factor out a p. They don't both share a p. But I can factor out a 16. In fact, I can factor out a minus 16 from both of them. So if I factor out a minus 16, I'm going to get this. And you can, again, check that by distributing. Minus 16 times p is minus 16p. Minus 16 times a positive 2, minus 32, equals 0. Now, if this works, if it's done correctly and it's in the right setup and everything works great, you should get the same thing inside the parentheses here, p plus 2 and p plus 2. Those two remaining terms should match. And that's important because what we're going to do now is we're going to look at this first group here as one big term. This is one giant term minus another term. So instead of just having this term and this term, these first two terms, and asking what can I factor out of these two terms, we're now looking at this as one big term, and this is one big term, and we're going to ask, what can we factor out of both of these terms? Well, since they both share a p plus 2, we can actually factor out this term, or this factor of p plus 2. This is what it looks like. So that's the mathematics behind it. That's what we're really doing, is we're factoring out a p plus 2, and what's left is 9p squared minus 16. What it looks like we're doing, this isn't mathematically correct, but it does appear that we're doing it this way, is we're taking the terms that match here, p plus 2 and p plus 2, and we're putting them together. And we're taking whatever's left over, and we're putting that together. Now, that's not mathematically accurate, but that's kind of what it looks like we're doing. And that does work. Like, if you look at it in that way, it works, and you'll get the right answer. What we're really doing is factoring out a p plus 2. factor of p plus 2. But that's how it kind of appears. So you can look at it in that way. Okay, so we're getting closer. We have p plus 2 equals 0. We've got two factors. We can use that zero product property. So p would have to be negative 2. Negative 2 plus p2 would equal 0. So that's one of the possible solutions. We're getting closer to the answer. However, this is not a linear equation here, or a linear function, 9p squared minus 16. So we can't just say, well, p would have to be something. We have to take this a little bit further. You could use the AC method, and you could try and factor this a little bit further. I also recognize that this is a difference, there's a subtraction here, a difference of perfect square numbers. I told you in chapter 1 that perfect squares were going to come up again and again, and that's very true. And here it is again. So 9p squared minus 16 is a difference of perfect squares, and it's going to factor to 3p minus 4 and 3p plus 4. And you can go back into chapter 1 and look at that video on difference of perfect squares. I think it was section 3 or 4, I forget, maybe section 4. But that's that difference of perfect squares. Now we have three linear equations. We can solve these now. So we've got p plus 2 equals 0, 3p minus 4 equals 0, or 3p plus 4 equals 0. One of those three has to be 0 to make this product equal 0. So again, p could be negative 2. Negative 2 plus 2 equals 0. If you solve this, if you add 4 to both sides, divide by 3, you'd get that p could be 4/3. If you solve this one over here on the right, you could minus 4, divide by 3, and you'd get that p equals negative 4/3. Try this one on your own, pause it, and see if you can get the right answer. I'm assuming you pause, I'm assuming you tried it on your own. Again, please do try it on your own before you look at the answers. These are the solutions. If you didn't get those solutions, or if you don't know how to do this, probably got stuck, watch the follow-up video. Just gonna check something here quick. Appears that we're still rolling just fine. Okay, so I'm gonna keep on going. You can read that. Those are the steps we just took. Okay, we'll look at a real-world situation. If your real world involves shooting an arrow off of a building. So here's our real-world problem. It's a tongue twister. An arrow is fired into the air. You can read it at your own pace here on top of a building. And we have this equation that they give us. So we don't have to come up with the equation for how an arrow flies through the air. It's given to us. Our question is, at what times will the arrow be 288 feet in the air? So we don't want to know when it hits the ground. That's not what we're concerned about. We want to know when will it be 288 feet up in the air. And this is our equations where t is time. So I'm going to move over to the document camera. Here it is. I've got my pretty picture here. So here's the idea, the concept. I've got an arrow. I'm shooting it off of a building. I'm hoping nobody's below. I don't want to know when it hits the ground. That would be 0. That I don't care about. I want to know when is it going to be 288 feet in the air. And I'm assuming it crosses that 288-foot threshold twice. It goes above 288 and then comes back below. I could be wrong. 288 could be exactly at the peak. It could be the maximum of that parabola, but we'll find out. I'm assuming that we're going to get